In this lecture, I will try to explain the concept generalized coordinates and configuration space. So, first consider the case of a free particle, a single particle, and to represent its position at any instant of time, we need a reference frame. Usually, the Cartesian coordinate system is used for representing the position coordinate of a single particle. We have a set of three axes x, y and z. The point where the three axes meet is called origin, and with respect to this origin we can specify this position of the particle as x, y, z. The meaning is that from origin the distance to this point parallel to the x-axis is x, and distance to this point parallel to y-axis is y, distance to this point parallel to z-axis is z. So we can specify the position of this particle by using these three Cartesian coordinates. We can say that they are position coordinates, and this space we can call it as a coordinate space, and it is now three-dimensional. Now consider the case of two particles. They are completely free, two free particles. At any instant of time, the configuration of the system can be specified by specifying the six Cartesian coordinates. Three Cartesian coordinates of first particle and three Cartesian coordinates of second particle. So there are total six position coordinates: x1, y1, z1, x2, y2, z2. Okay, by specifying these six coordinates, we can specify the configuration of this particular system at any instant of time. The two cases I considered here are free systems, that is unconstrained systems. Okay, for unconstrained system, the position coordinates are independent and equations of motion can be written in terms of position coordinates. What is the meaning of position coordinates are independent? As time changes, the configuration of this particle can change. If it is a moving particle, as time changes, these coordinates will change. And with respect to time, this point will curve out a trajectory, in this three-dimensional space. And suppose at a later time, the particle is at this point. From this point to this point, particle can take any trajectory. Okay, there is no restriction for any of this trajectory. All these trajectories are possible. That is the meaning of the position coordinates are completely independent. The particle can go from the configuration at one instant to the configuration at a later instant through any of the path. Okay, there is no restrictions to any of these paths. Now, consider a constraint system. If there are constraints in the system, then the position coordinates will not be independent. Then we will define a new set of coordinates which are all independent. That set of independent coordinates required to specify the configuration of a dynamical system are called generalized coordinates. Okay, this set of independent coordinates required to specify the configuration of a dynamical system are called generalized coordinates. And for an unconstrained system, the number of position coordinates and number of generalized coordinates will be exactly the same. For a constrained system, the number of generalized coordinates will be less than number of position coordinates. That I will explain in the coming examples. So consider a constrained system. Consider a particle which has two constraints. One is the z coordinate should always be 0. That is, the motion is restricted only in the xy plane. And there is one more constraint: x square plus y square should always equal to r square. X square plus y square should always equal to r square. So there are two constraints. So the free particle now constrained to move only along the surface of a circle, of radius r and centered at origin. So this green one is the particle. The position at any instant can be represented by the coordinates x and y. But since there are two constraints, z equal to 0, x square plus y square equal to r square, both are holonomic constraints, both are expressed as equations. So degree of freedom of the system will be 3 into 1. There is one particle in 3-dimensional space, that is why it is 3 into 1 minus 2 holonomic constraints. So this becomes 1. General expression is 3n minus k. So to specify the position of this particle, we need to specify two numbers. I can represent the position with x and y, but the problem is x and y are not independent. They are not independent. They are related by this equation. X square plus y square is equal to r square. So no need to specify both the numbers. Okay, you just specify x or y. But is it possible, if you specify x, is it possible to find uniquely the value of y? No. Because if x is given, using the equation, we can write y as plus or minus square root of r square minus x square. Plus or minus. So for each value of x, there will be two values of y. There will be two values of y. That is, y is not unique. So there is no point in specifying x alone. Okay, we cannot find a suitable y, because for a particular x value, for suppose this is the x value, we can have y value this point or this point, directly below this point, plus or minus y. So x is not a suitable choice for representing the position of particle, because once we know x, we cannot solve for y uniquely. So what will be a suitable choice for a single coordinate? We know that for specifying the position of a particle in a plane, we can use plane polar coordinates also. What are plane polar coordinates? The distance from origin to that point is r, and the angle between r and the positive x-axis is theta. We can represent r and theta for specifying the position of particle. So instead of x and y, we can use r and theta also. Here, when particle moves along a circle, r is fixed. R is fixed. So with this constraint, there is no need to specify the value of r at each point, because it is already fixed. It will not vary. So to specify the configuration of this particle at any instant, you just specify the angle with the x-axis. Okay. So if you mention that the angle is 45 degree, one can draw a circle. With the knowledge of this constraint, one can draw a circle of radius r, and the given information is theta value is 45. Then you can uniquely represent the position of the particle. So by specifying theta, we can specify the position of particle. So theta can be taken as the generalized coordinates. The independent coordinate required to specify the position of particle which is moving along a circle is theta. Okay, so this is known as a generalized coordinate. Okay, theta is the generalized coordinate for this case. We will consider the next example: a particle moving along a straight line. A particle moving along a straight line. Degree of freedom is 1, because there is no variation for y coordinate, z coordinate. When the particle moves, only the x coordinate changes. There is only 1 degree of freedom. And the generalized coordinate, you can take it as the x coordinate of this particle. The x coordinate of this particle. Consider a particle moving in a 2-dimensional plane. A particle moving in a 2-dimensional plane. At any instant of time, its position can be represented either by the Cartesian coordinates x, y, or by the plane polar coordinates r, theta. In both cases, the number of coordinates are same. There are two Cartesian coordinates x and y, 2 plane polar coordinates r and theta. So degree of freedom is the number of independent coordinates required to specify the state of a system, and it is 2 always. That is unique. Degree of freedom is unique. But the generalized coordinates, the choice of generalized coordinates is not unique. You can choose the Cartesian coordinates x and y, or you can choose the plane polar coordinates r and theta. So the important point is, for a particular dynamical system, the choice of generalized coordinates is not unique, but the number of generalized coordinates is unique, and the number is equal to degree of freedom of the system. Consider next example, a bead sliding down a rod. A bead sliding down a rod. Suppose this is x-axis, this is y-axis. A rod is inclined at an angle alpha with the positive x-axis. A bead is moving along this rod. The position of this bead at any instant can be represented by the Cartesian coordinates x and y, but they are not independent. This is a constrained system. The bead is constrained to move only along this rod. The constraint is tan alpha is equal to y by x. So we can write y is equal to x tan alpha. It is a holonomic constraint that will reduce the degree of freedom. So degree of freedom is just 1. Okay, degree of freedom is just 1. No need to specify both the coordinates. Here, generalized coordinate can be either x or y, because given x, you can find y using this expression, or given y, you can find x using the expression x is equal to y cot alpha. Y cot alpha. So, it is enough to take either x or y as generalized coordinates. Okay, but in the case of a particle moving along a circle, x or y is not a suitable choice of generalized coordinates, because given x, we cannot find y uniquely because there are two values. But in this case, no problem with x or y. With given x, we can specify y, or given y, we can specify x uniquely. Consider another example, simple pendulum. For simple pendulum, the constraint is length of the string is constant. Again, the position of bob can be represented by the position coordinates x and y, but they are not independent. They are related by this expression x square plus y square is equal to L square. But x or y cannot be taken as the generalized coordinate, because if x is given, y cannot be found uniquely. Okay, y cannot be found uniquely. Therefore, x or y is not a suitable choice for generalized coordinate. A suitable choice is the angle made with vertical. The angle made by the string with the vertical direction, you can choose it as a generalized coordinate theta, or you can choose the angle from the horizontal x-axis to the string, that is phi. This is also a suitable generalized coordinates. No problem with this also. It is, you cannot take the angle with the vertical, or you can take angle with the horizontal. Okay, both these are suitable choices for generalized coordinates, but x or y is not a suitable choice for generalized coordinates, because given x, you cannot find y uniquely. Now consider the example of spherical pendulum. Spherical pendulum. Here you have a bob attached to a string. The other end of the string is fixed at this point, say origin of a coordinate system. But this bob is not restricted to move only in a plane. It can move anywhere in the three-dimensional space, keeping the length of the string constant. So here the constraint is x square plus y square plus z square is equal to L square. If L is the length of the string, then the constraint is x square plus y square plus z square is equal to L square. Therefore, degrees of freedom is 3n minus k, that becomes 3 into 1 minus k is 1. So, degrees of freedom is 2. We need two generalized coordinates. We need two generalized coordinates. Can we take x and y as generalized coordinates? No, because given x and y, z value is not unique. Z value is not unique. Given x and y, z will have two values, plus or minus. Okay, so either of these coordinates are not a unique choice of generalized coordinates. I can choose the spherical polar coordinates, that is the angle with the z-axis theta, as one of the generalized coordinate, and the projection of this L on the xy plane, that is this green line, makes an angle phi with the positive x-axis. This phi and this polar angle theta you can choose as the generalized coordinates. Okay, a suitable generalized coordinate for spherical pendulum is theta and phi. Theta and phi. By specifying theta and phi, we can specify the position of this bob at any instant of time t. Okay. Now consider the case of planetary motion. This is sun. A planet is moving in an elliptical orbit around the sun, and the position of planet at any instant of time can be specified by specifying the radial distance from the sun r and the angle theta with the positive x-axis. So if this is x-axis, we can specify the angle theta. So a suitable generalized coordinates for planetary motion are r and theta. Okay, so these are the examples for generalized coordinates. I will give you more examples. Consider a dumbbell. Dumbbell means two masses connected by a rigid rod. This mass has position coordinates x1, y1. This mass has position coordinates x2, y2. The length of this rod is fixed at L. So there are two particles, one constraint. So degree of freedom is 2 into 2 minus 1. Here, since the motion is in a two-dimensional plane, the equation for finding the degree of freedom is 2n minus k. N is 2, so 2 into 2 minus 1. So degree of freedom is 3. There will be three generalized coordinates for this system. What are the generalized coordinates? What is the suitable choice? I can choose the center of mass coordinates x, y. And the angle, say theta, with the vertical. For the angle between the vertical and this length is theta. So one of the choice is x, y and theta. This is a suitable choice for generalized coordinates. Or you can take the coordinates of this mass x1, y1, this mass x1, y1 and this angle theta as the generalized coordinate. Or you can take this mass x2, y2 and this angle as generalized coordinates. Or you can take x1, y1, the coordinates of this mass and the angle with horizontal as the generalized coordinates. So there are a lot of choices for generalized coordinates. The only thing is, number of generalized coordinates will be unique. You need minimum 3 coordinates to specify the state of this system. Okay. For example, if you say that the first particle has position coordinates, 2, 3, then it means that particle is at the position 2, 3. So the particle is at this point. And you know from the constraint that distance between the masses, is 3. Okay, if it is 3, then one can say that the second particle is at a distance of 3 along this direction. One can say that the second mass is at this position, and one can say that the second mass is at this position 3 meters from this first particle. One can say that the second particle is at this position. One can say that the second particle is at this position. Second particle can be anywhere on this circle of radius 3 and centered at the first particle. Okay, so in order to specify it uniquely, we need one more coordinate. With the two coordinates of this masses, we cannot specify the configuration of dumbbell. uniquely. In order to specify that, we need one more coordinate. Suppose I specified that the angle with the vertical is 45 degree, angle with the vertical is 45 degree, then the configuration is unique. From the first mass, you draw a line of 3 meter at an angle of 45 degree with the vertical, then you can mark the second mass there. So the configuration of dumbbell is unique by specifying 3 coordinates. And that choice of coordinates is not unique. That will vary. Now consider this system. There are 2 masses. This first mass M1, that is restricted to move only along the x-axis. Second mass M2, which is connected to the first mass by a rigid rod, and this M2 is free to move in this xy plane. So you have a system of 2 masses. First mass is restricted to move only along the x-axis. Second mass is connected to the first one using a rigid rod. This length is fixed, and the second mass can move in this 2-dimensional plane, xy plane. How many degrees of freedom? For this system? There are 2 particles, and it is a 2-dimensional case. So equation of finding degrees of freedom is 2n minus k. Number of particles is 2. 2 into 2 minus, what is the number of holonomic constraints? One constraint is y1 is equal to 0, because the first particle is restricted to move only along the x-axis. Its y coordinate is always 0. So y1 is equal to 0 is one of the constraint. Second constraint is x2 minus x1 the whole square plus y2 minus y1 the whole square equal to L square. Distance between 2 points x1 y1 and x2 y2 is given by square root of x2 minus x1 square plus y2 minus y1 square, and that distance is now L. So this constraint, you can express it mathematically as x2 minus x1 square plus y2 minus y1 square equal to L square. This is a holonomic constraint. This is also a holonomic constraint. So there are 2 holonomic constraints. So degrees of freedom will be 4 minus 2. What are the generalized coordinates? I can choose generalized coordinates as x1 and theta. Theta is the angle with the vertical. By specifying these 2 numbers, we can specify the configuration of the system. For example, if I say that x1 is equal to 5 and theta is equal to 90 degree, if I say that x1 is equal to 5 and theta is equal to 90 degree, then we can say that the first particle is at a distance of 5 meters from the origin. This is first particle. This is unique. Second particle, I mentioned that x1 is 5 and theta is pi by 2. And we already know that length of the rod is say 3 meter. This is the constraint. This is already given, and these are the generalized coordinates x1 and theta. Once we specified the values of x1 and theta, the configuration of the system is uniquely specified. The second mass will be at here, because it is at an angle of 90 degree with vertical. This is vertical direction. This angle is pi by 2. So the second mass is somewhere here. Okay. So it is uniquely specified by specifying the 2 numbers x1 and theta. So these are the generalized coordinates for this system. So generalized coordinates are the set of independent coordinates required to specify the state of a system or configuration of a system uniquely. Usually the generalized coordinates are represented by the symbol qj where j can take values 1, 2, 3, etc. up to small n, where small n is degrees of freedom of the system. That is, if a system has small n degrees of freedom, then there will be small n number of generalized coordinates, and I can denote the generalized coordinates as q1, q2, q3, etc. up to qn. This is the representation of generalized coordinates, and we can say that for this example q1 is x1 and q2 is theta. And for the example of dumbbell, I can say that q1 is x, q2 is y, the position coordinates of center of mass, q3 is theta. And for planetary motion, we can say that q1 is r, q2 is theta. These are the generalized coordinates. For spherical pendulum, I can say that q1 is theta, q2 is phi. And for simple pendulum, I can say that q1 is theta or phi. For a bead sliding on a rod, I can say that q1 is x or y. Okay, for a particle moving in a two-dimensional plane, I can write q1 as r and q2 as theta. For this case, particle moving in a one-dimensional line, q1 is simply x. And for this particle, we can say that q1 is theta. For a particle moving along a circle, generalized coordinate is theta. And for unconstrained system also, we can write the generalized coordinates. Here for these two particles, which are completely free, I can say that there are 6 generalized coordinates, and I can represent them as q1 is equal to x1, q2 is equal to x2, q3 equal to x3, q4 is equal to not x1, x2, x3, they are x1, y1, z1, the position coordinate of first mass, q4 as x2, q5 as y2, q6 as z2. And for this first case, I can say that the generalized coordinates are q1 is equal to x, q2 is equal to y, q3 is equal to z. So generalized coordinates and position coordinates are different only when there are constraints. If there is no constraints, position coordinates are also generalized coordinates, and the number of position coordinates and number of generalized coordinates will be same for unconstrained system. If there is constraints, number of generalized coordinates will be less than number of position coordinates, and that number is equal to degrees of freedom of the system. Okay, this is all about generalized coordinates, and I think it is clear. Now we will discuss about configuration space. Configuration space is the one spanned by generalized coordinates. Okay, it is the space spanned by generalized coordinates. We will explain this concept using different examples. Consider first the case of a particle moving in a circle. Okay, for a particle moving in a circle, we already seen that we need one generalized coordinate to represent its position uniquely, and that is theta. So generalized coordinate is theta for a particle moving along a circle. So the configuration space is one dimensional, and you will have one axis, and it will have some origin. Okay, and theta is marked on this axis. You can have values theta is equal to pi by 2, pi, 3 pi by 2, 2 pi, etc. Okay, so configuration space is one dimensional. One dimensional configuration space is for particle moving in a circle. We have only one generalized coordinate, and that is theta. So you have to mark theta on one axis. That is the generalized, that is the configuration space. Okay. Now consider a particle moving along a straight line. Again, particle moving along a straight line means there is only one generalized coordinate. So configuration space will be one dimensional, and you will have one axis on which the generalized coordinate x is represented. You have some arbitrary origin, and towards right you have 1, 2, 3, 4, 5, etc. Towards left you have -1, -2, -3, etc. At any particular instant, particle will be any of this point. Particle will be at any of these points. Consider a particle moving in a two-dimensional plane. Two-dimensional plane. Then the configuration space can be either the xy space, because for a particle moving in two-dimensional space, we already seen that we can use either Cartesian coordinates x and y as the generalized coordinates, or the polar coordinates r and theta as the generalized coordinates. So we can draw a configuration space by plotting x and y on two axes, or you can plot r and theta on two axes to represent the position of particle at any instant of time. So configuration space can be either the xy Cartesian space or the r theta plane polar coordinate space. Okay. Now consider the example of simple pendulum. Again, for simple pendulum, degree of freedom is 1. So only one generalized coordinate, and that is theta. So the configuration space is one dimensional configuration space, and on that axis you have theta. Okay. We can represent various values of theta. Rightward values are positive, pi by 4, pi by 2, etc. Leftward values are negative, minus pi by 4, minus pi by 2, etc. At any instant of time, the bob will be at any one of these points. Okay. Spherical pendulum. Spherical pendulum, degree of freedom is 2. Generalized coordinates are theta and phi. The spherical polar coordinates theta and phi are the generalized coordinates. So the configuration space will be two-dimensional. On the two axes, you have theta and phi. Theta values you can mark it as 0, pi by 2, pi, etc. Phi values also can mark it as 0, pi by 2, pi, etc. Okay. So spherical pendulum, the configuration space is two-dimensional. At any instant of time, suppose the particle is at this point, that means that theta value is somewhere here, okay, 3 pi by 4, and phi value is, so this represents a particular configuration of the system. That is why it is known as configuration space. Now for planetary motion, you have degree of freedom 2, generalized coordinates r and theta. So the configuration space will be two dimensional configuration space. On two axes we have r and theta. Now for a dumbbell moving in two-dimensional plane, degree of freedom is 3, that we already discussed, and generalized coordinates are x, y, and theta. So configuration space will be three-dimensional. We will have three axes. On one axis you have x, the other axis you have y, and in one axis you have theta. Okay, theta. This is the configuration space of a dumbbell, which is restricted to move in a plane. The next example is two masses. One mass is constrained to move along the x-axis only. The other mass is connected with the first mass with a rigid rod, and it is free to move in the plane. Now we have 2 degrees of freedom, and generalized coordinates are x and theta. So the configuration space will be two-dimensional. On one axis you have x, and the other axis you have theta. Now the important point is, for constrained system, all points in position space are not accessible to the system, but all points in configuration space are accessible to the system. What is the meaning of this? I will explain that. Consider the case of a simple pendulum. And if you plot the position space x, y space, you have a simple pendulum, a string with a bob attached to it, and you have two axes. Horizontal axis is x, vertical axis is y, and you can represent the position of particle at any instant as x, y. The length of the string is fixed, it is L. So in the position space, this bob cannot have any arbitrary values of x and y. The bob can take only those values of x and y which are lying on a circle of radius L. Okay, if you consider a circle of a radius L, then the position of bob at any instant of time can be any one of the point on this circle. Okay, this point is not allowed for the bob. This point is not allowed for the bob. This point is not allowed for the bob. This bob can move in a circular arc of radius L. So only these points are allowed for the bob. So that means not all points on the position space are accessible to the system. But if you draw the configuration space of this system, here the configuration space is actually one dimensional, and the you have to mark theta on that axis because configuration space is space spanned by generalized coordinates. So here you have pi by 2, pi, etc. Here you have minus pi by 2, minus pi, etc. And if the particle is somewhere here, that is at an angle of say pi by 4, at an angle of say pi by 4, you can represent it somewhere here, it is pi by 4. If the bob reaches here at an angle pi by 2, you have that point here. So all points in this line, all points in this line are accessible to a system. We can say that it is restricted between minus pi and pi because after one complete rotation it will again starts from 0. Okay, so you can say that when it reaches the topmost point it is pi, and when it reaches the this side topmost point it is minus pi. Okay, but from minus pi to pi all the points are accessible to a system. All the points are accessible to a system. Similarly, if you consider a particle as bob of spherical pendulum, if you consider the bob of a spherical pendulum, then the position space is xyz space, and not all points on this space are accessible to a system. Only the points which lying on the surface of a sphere are accessible to a system. Only points on the surface of a sphere are accessible to a system. But if you plot the configuration space of the same system, that is a space spanned by theta and phi, a space spanned by theta and phi. Theta can take values from 0 to pi, any value from 0 to pi. Phi can take any value from 0 to 2 pi because phi is azimuthal angle, theta is polar angle in spherical polar coordinates. So all points in this limit is accessible to system. All points are accessible to system from 0 to pi and from 0 to 2 pi. Okay, theta value from 0 to pi and phi value from 0 to 2 pi. All the points in configuration space are accessible to system. But in position space, only the points on the surface of a sphere are accessible to the system. Okay, so that is the meaning of this statement. For constrained system, all points in position space are not accessible to the system, but all points in configuration space are accessible to the system. For a system of n degrees of freedom, for a system of n degrees of freedom, there will be n generalized coordinates, and the configuration space will be n dimension. Configuration space will be n dimension. Any point on the configuration space, can be represented by specifying the n values q1, q2, q3, etc. qn. In general, on the axis you are marking generalized coordinates. Okay, for configuration space on the axis, it is generalized coordinates q1, q2, q3, etc. Only 3 dimension I can represent like this. From 4 dimension onwards, you have to imagine that for a system of n degrees of freedom, the configuration space will be n dimensional. Any point on that n dimensional space will have n coordinates. In this 3 dimensional configuration space, any point will have 3 coordinates q1, q2, q3. So in an n dimensional configuration space, any point will have n coordinates q1, q2, etc. qn, and that represents the configuration of the system at any particular instant of time. That is why it is called a configuration space. And the most important point is all the points in the configuration space are accessible to a system because all these coordinates are independent of each other. All these coordinates are independent of each other. But in the case of position coordinates, if it is a constrained motion, the position coordinates are not independent of each other. So all the points in the position space are not accessible to a system. Then the idea is define a set of generalized coordinates and define a new space which is spanned by the generalized coordinates, and that is the meaning of configuration space. Thank you.